I guess we can start now. Hello, everyone. Welcome back. So we'll start our participants' presentation sessions. There will be three presentations. Each one will take 15 minutes with 5 minutes of questions and answers. Our first speaker is Matthew Staab from University of California, Davis. And his presentation's title is A Method for Improving Utility of ARPES Datasets on Quantum Materials. Okay, so please.
Can you hear me fine? Yeah. So thanks to the organizers for letting me talk. There's a lot of really great abstracts. I'm glad to be able to share my little passion project here. And special thanks for letting me follow up Professor Yee's presentation, where she did a great explanation of ARPES that I don't now need to do again. So I'm a postdoc with Ina Vishik at UC Davis, and this talk's going to be a little bit different, more meta perhaps, because we've had a lot of intense theory and experimental stuff about topological and correlated materials so far. This talks more about a method to improve ARPES so that we can do more ARPES on topological and correlated materials. So maybe it'll be a little refreshing in that sense. So I want to go through a little example data set of a quantum material that I did a lot of work on during my PhD, just to sort of orient us for the rest of the talk. So this material is called lanthanum nickel gallium 2. It has some fancy non-symmorphic symmetries, a screw symmetry, and a mirror plane, which cause these Dirac lines and loops along this plane of the Brillouin zone. And for a lot of my work with this, I took sort of a broad photon energy dependent ARPES data, and even cleaved in multiple orientations to get the electronic structure across the whole 3D Brillouin zone. So I just want to call out a couple of things about this data set, where if I take a certain KZ slice, we get a sort of hexagonal zone. And with that hexagonal zone, then the zone's going to tile offset. So an ARPES cut will be tiling across multiple zones in sort of a special way. That'll be important later. Okay, so I won't go through the basics of ARPES again, where we have we're measuring the perpendicular parallel momentum and kinetic energy to get binding energy and the dispersion relation. But what I do want to talk about, sorry, my clicker's not clicking forward here, is the perpendicular momentum component a little bit. So as the electron gets ejected from a material, it has to overcome some inner potential to escape the material. There's a little bit of a nomenclature issue where this, when we're talking about the kinetic energy, there's just a work function that it has to escape. But when we talk about the momentum, we call it an inner potential, which is a slightly different quantity with something in addition to the inner work function. So in the perpendicular direction, we don't have quite as simple relationship between angle and momentum as the parallel direction. We have this cosine squared term with the kinetic energy and just another offset due to this inner potential. And you can actually derive this using like simple classical mechanics kind of ideas, where you have a step potential in the direction of emission. Okay, and the other important thing is, because of this dependence on the kinetic energy, we can tune the photon energy to measure different perpendicular momenta in the Brillouin zone. And this inner potential has a big effect on the spectra in many ways. And it's sort of comes from this free electron approximation. So in ARPES, we're taking an initial state in the material. This is the thing everybody studies with DFT, all the bands. And we're transitioning that electron to essentially an ejected free electron. So there's some matrix that encompasses the incident photon, determining that interaction to eject the electron. And that final state we assume is a free electron. So it's a parabolic dispersion like this. But because of this potential offset, it can have an offset V naught here. And essentially this V naught in most ARPES people's minds, it's a phenomenological parameter that you just find the best value that agrees with the data, and that's how you get it. But it's sort of a matching condition to allow this transition from the band structure up to this free electron state. And so a little aside about that, here's an example of a large photon energy dependent data set on a 2D material tungsten ditelluride from this paper here. And they're using very high energy photons, so it's kind of softer X-rays. But you can see a little bit of periodicity in the Brillouin zone, which they've colored in gray lines here. That's sort of the small wiggles. But there's like a broad intensity periodicity that's like many Brillouin zones. So this can actually be explained with like some very nice, simple quantum mechanics ideas. So I wanted to go through it real quick. If I look at this separation from, say, the peak intensity towards maybe like a half max or like a 1 sigma, if I had to estimate this as a Gaussian, it's like sort of 0.6 to 0.9 inverse angstroms. And if I think about the electron that I'm ejecting, and I estimate it with some kinetic energy of 1/2 mv squared, that velocity I can convert to speed in angstroms per attosecond. And I can estimate sort of the distance that that electron could travel before that final state is no longer like a valid state, before it's like it's been ejected. So it's sort of like a lifetime. And if that distance is around an angstrom, then with a velocity coming from a 600 eV photon, it's like 6 attoseconds before that, for like that lifetime. And using Heisenberg uncertainty principle, we can get that the bandwidth of that final state should be around 55 eV, which corresponds pretty close to this scale of the intensity variation here. So I think this is kind of like a nice representation of some simple physics showing up there. Okay, so how do people determine the inner potential in like regular ARPES experiments? First, they can do this photon energy dependent ARPES and try to pick out this periodicity. This is good, but takes a lot of experimental time to collect well. You have to use very valuable synchrotron beam time and scan across lots of photon energies. Another method is to sort of take a much smaller range of photon energy and compare it with some DFT calculations. So you're essentially shifting what you think the inner potential is on your data until your eye says that it matches the bands well, which is also good because it saves time, but has sort of a human error problem where you can be off by a few EV because a few EV doesn't shift the band very far. Okay, another way, which is something I did before, is cleaving in multiple orientations. So if you assume that the inner potential is the same depending on the cleave orientations, you can have a platelet sample that you cleave like this, and you measure some photon energy, or you measure some spectrum coming off this way. But if your platelets are thick enough, you can actually mount them sideways and cleave the thin edge. And you have to do some careful alignments to make sure you have a high symmetry plane there. But you can take photoemission from that spot, and kind of gives you 2 different data sets to align the inner potential with. The last thing you can do, which some people do, is just guess, because usually around 15 eV is about right. And there's plenty of good work that's been done where you just guess a reasonable number. Okay, so ARPES probes spheres in momenta. So a lot of times we'll talk about in ARPES a planar cut, or we'll overlay our data from DFT as if it's on a plane. But in reality, it's actually probing a sphere in the initial momentum space. So if you take these two, the parallel and perpendicular momenta, and you square them, add them together, you get this as some constant. This is the radius of the sphere that you're probing. And it's a little bit complicated parameterization of the sphere because of this inner potential, but it is still a sphere. And if I compare that to what a planar cut looks like, sort of zoomed in, you can see this blue line. Frequently, if you're getting some DFT calculations from a collaborator and you're doing some ARPES, you'll plot the DFT from the blue line on top of your ARPES data from the red line. And usually we'll be studying some particular spot in momentum space. So maybe we'll only zoom in and care about this region here. But in that case, we end up throwing away some data that ends up being useless. So part of my project's goal is to make this further out data be more useful. And one way to do that is to use the symmetry of momentum space. So we have this quantized or discrete translational symmetry, and that in momentum space looks like a tiling Brillouin zone. So I'm showing the same plot here, but one with that lanthanum nickel gallium 2 Brillouin zone overlaid. So you can see this single cut of ARPES would probe sort of a second Brillouin zone over here and another over here, whereas most people would just use this data from the interior here when they're actually presenting it on a paper. And this ends up kind of just being wasted extra spectra on the right. Okay, so the core idea of my project is to then take that data and project them all into a single Brillouin zone. So here I'm showing a sort of rainbow of photon energies from 110 up to 144. And on the right, I'm showing where all those spectra are now projected into the first Brillouin zone. And you can see that there are locations where they overlap. So for example, here there's some orange bands that are overlapping with some green bands. So this is different ARPES measurements that are actually measuring the same spot in momentum space. And the effect of the interpotential on this projected data is kind of interesting because the interpotential, if you think back to the perpendicular momentum equation, kind of has the same sign as the photon energy. So it's going to shift our data up and down. And so if I play this and sort of sweep through some values, it sort of shifts around the data, right? Well, this is changing what ARPES data are next to each other in momentum space. So now instead of me showing just the cut or like the location of the ARPES data, now I want to show the like a Fermi surface on that ARPES data. So this is a made up data set when I was just like coming up with the idea of this project, where on the left I'm showing some reconstruction of a Fermi surface using an interpotential of 0, and on the right I'm showing it with an interpotential of 14. And if I play through, you can sort of see this broken, bad looking picture turn into a nice picture at the correct interpotential and then break up and turn bad again. And so this is sort of the core of my project, where I'm going to take the ARPES data at all these different photon energies, all these different angles, project them into the first Brillouin zone and compare sort of the co-located EDCs. So EDC is a ARPES term for the intensity of the spectrum at a location in momentum space. So here I've shown just a single ARPES cut, doesn't matter where, but this green line is a clearly different place in momentum space than the red and the blue, but the red and the blue are symmetric. So the red and the blue should have the same spectrum. And if I plot the intensity of just these three lines here, you can sort of clearly see it with your eyes that the red and the blue are probing the same spectrum, whereas the green is not. Now, I'm going to take differences between these three data sets. So the difference between the red and the blue is shown in black here, the sum or the squared difference, whereas the difference between the blue and the green or the red and the green are shown here in red and blue. And you can like, it's sort of saying an obvious thing, but they're very different, right? Where the spectra disagree, there's a lot of sort of squared differences, whereas where the spectra are similar, there's not as much difference. It's kind of just noise. So I'm going to extend this and apply it to that entire sort of three-dimensional data set. Now, all the pictures I've shown here were sort of two-dimensional slices through momentum space, but my data set, remember, is sort of an angle in this direction and an angle in this direction and photon energies in that direction. So I have like this three-dimensional momentum data set that I'm projecting into the Brillouin zone. And if I plot the sum squared differences out of every close by crossing in the zone as a function of interpotential, I get a curve like this, 1 minute? Okay. So you can see that there's clearly an inner potential where the sample agrees with itself the most. And this is what I'm claiming is a way to determine the inner potential with just ARPES data without needing any sort of exterior information. And so here I'm showing a little bit of a Fermi surface reconstruction across different inner potentials. And it turns out that this is better if you have sort of large range of photon energies sparsely rather than a dense small amount. So if I use half the data but spaced out larger, I still get a reasonable answer. Whereas if I space it out too far or only use the top or bottom half of the data set, it turns into pretty noisy and bad. If I show now a different material, the cerium cobalt germanium 3, this is Robert Prater has a poster out there if you want to get into the details of this material, but it's got a lot more complexities to the data set. And the result is pretty good because it does reproduce a minimum at the inner potential that Bobby has identified, but it has some other minima that are interesting in their own right. And I have some reasons here, but I'll hold back on discussing them for time, and we can have some questions.
Thanks for the speaker. We maybe have like time for 1 or 2 questions.
Thank you for the nice talk. I just have one question, just follow up with the last point. You showed that for different materials, because of matrix element effect, sometimes you get more complicated profile here. So when you do the measurements, when you prepare to use this method to analyze the inner potential, is there a preferred like polarization you would use, or how do you comment on that?
So for this current implementation, a polarization that's not symmetric with your materials geometry seems to be preferable because you don't get as much like strong matrix element effects. The material that Bobby is studying has like really bright matrix element effects. The bands on the left and the right look completely different. And also it has sort of a magnetic band folding maybe because of these extra bands that are showing up. But it's got a lot of more complexities going on in that data set, whereas the lanthanum data set was much more straightforward and less matrix element effects, but still a very complicated 3D electronic structure.